Hey everybody, how you doing today? Today we're going to cover 5.3 in trigonometry. This is effectively like 1.3 for a different college, but at colleges as a quiz, at least in my class, I use a merge between college algebra and trigonometry textbook, and the trig chapters are 5 through 8. So before we get started on 5.3, let's give you a little warm-up related to yesterday's work. And this is similar to what we ended up doing last problem, using identities to find functions or trig values. Find the trig values. So our example, find sine theta and cosine theta given that tangent theta equals -3/2. Sorry, +3/2. And theta is in quadrant 3. This means an element of or is in, theta is in quadrant 3. So how can we go about doing this? Well, we know tangent theta equals y/x, and that's sine theta over cosine theta. And in this problem, it's 3/2. Now, you may be inclined to try to just pull these and make these a triangle. Y = 3. If you try to say sine theta equals 3, though, well, and cosine theta equals 2, well, is that even correct? In quadrant 3, this is Q1, Q2, Q3, Q4. Q3, everything's negative over here. So that would have to be like -3 and -2. So we're going to have to change that. Make this -3 over -2. Does this still work though? No, this does not work. Why? Do you know why? Think about it for a second. See what you come up with. Hit pause. Now, the problem with this is sine theta equaling -3. Well, recall sine theta had to be between -1 and 1. This doesn't work. This doesn't fit. So we actually have to use the identities. I suppose you could say it's y and x. Y equals -3, x equals -2, and go from there. Find r and stuff that way. But let's use the identities. I'll make a note of that though. We could say y equals 3, x or -3, x equals -2. It's not a unit circle. Calculate r with x squared plus y squared equals r squared and find the values. Let's use identities though. Let's use identities. So pause it. I'm going to flip the page and we'll go from there. Okay. So let me write again. We've got tangent theta. I'm going to say -3 over -2, with theta is in quadrant 3. So what were our identities that we had? We recall we had sine squared theta plus cosine squared theta equals 1. We had tangent squared theta plus 1 equals secant squared theta. And we had 1 plus cotangent squared theta equaled cosecant squared theta. What were we trying to find here? Find sine theta and cosine theta. And that's why we didn't want to go with it being the unit circle, just pulling it across and saying sine theta equaled 3 or 2, -3 or -2. That would have worked if sine theta or cosine theta could have been 3 or 2. It doesn't. We have tangent though, so let's use this one. So we've got tangent theta is -3 over -2, or 3/2, and we're going to square it. We're going to add 1 to it, and that has to equal secant squared theta. If we square this, this is 9/4 plus 1. I'm going to write this with the common denominator of 4. 1 is 4 over 4. And 9/4 plus 4/4 is 13/4. Recall secant theta is 1 over cosine theta. So in quadrant 3, cosine theta is less than 0. So secant theta is less than 0. That's going to matter when we take the square root. Boom, boom. Secant theta equals the square root of 13 over the square root of 4, which is 2. In quadrant 3, though, we're going with negative. That's not what we wanted, though. We didn't want secant theta. We wanted cosine theta. So let's flip it. Cosine theta is -2 over square root of 13. And when we rationalize it by multiplying by radical 13 on top and bottom, we get -2 root 13 over 13. So that's cosine theta. Putting it somewhere so I can box it where it's nice and pretty. That's one of them. We need sine theta. I'm going to go with the top equation now. We have cosine. Let's use it. Sine squared theta plus cosine squared theta. Let's use this version right here. -2 over square root of 13 squared equals 1. Sine squared theta plus 4 over 13 equals 1. I'm going to write it as 13 over 13 because I need to subtract 4/3 from both sides. And we get sine squared theta equals 9/13. And in quadrant 3, sine is less than 0 also. In Q3, so it's going to be negative when we take the square root. Sine theta equals negative, square root of 9 is 3 over the square root of 13. And if we rationalize it, -3 root 13 over 13. Again, I'm doing that by multiplying the top and bottom by the bottom. That clears radical signs in the denominator. All right, good stuff. Let's take a look at 5.3. .3 is on triangles and reference angles. Okay, under triangles, let's start with right triangles. In right triangles, we have the good old SOHCAHTOA. We'll call, well, this is side A, side B, side C. We tend to use lowercase for the sides. And capitals for the opposite angles. So the opposite for A is this angle here, and we're going to use capital A. The opposite, that looks like a music note right there. Let's do that. The capital B, the opposite angle is that one, and that makes C our right angle, which we know is 90 degrees. Let's say our triangle, we have 16, 30, and 34. And let's call this one angle A, that one angle B. I want to point out something to you. Let's use our SOHCAHTOA. Ooh, I'm just rotating all up. Let's use our SOHCAHTOA. Sine of A is opposite over hypotenuse. I'm not going to reduce because it's, we can if we need to, but it's not where I'm really heading with this argument. Cosine of A is adjacent over hypotenuse, or it's not really where I'm heading with this discussion. If we look at sine of B and cosine of B, B, the opposite is 30, the hypotenuse is 34. And adjacent for B is 16, the hypotenuse is 34. So A over H. And you'll notice sine of A is equal to cosine B, and cosine A is equal to sine of B. And if we look at the tangents, tangent A is opposite over adjacent. Tangent of B is 30 over 16, which is really cotangent of B, right? Or cotangent of A. Well, that's interesting. Well, why is this working the way it does? Well, something you need to know, the sum of the angles in a triangle equals 180. Interior angles, the ones inside of a triangle, equal 180 degrees. Okay, hit pause if you need to. I'm going to use that sine A and stuff up there, so maybe I'll keep that. Well, no, I don't need to. What we had going on up there was we had sine A equaled cosine B, cosine A equaled sine B, and tangent A equals cotangent B, or cotangent of A equals tangent B. We said the sum of the angles have to add to 180. A plus B plus C had to equal 180 degrees. but we know C is 90 degrees. We subtract 90 from both sides. And we get A plus B equals 90. Or B equals 90 degrees minus A. Okay. This leads us to our cofunction identities. The sine of A is equal to cosine of B, but B is 90 minus A. Cosine of A equals sine of B from here, but B again is 90 degrees minus A. Tangent A equals cotangent of B, which is 90 degrees minus A. Those are our base three. We also have cosecant. We just flip each of these over. Cosecant A equals secant of 90 degrees minus A. Secant of A equals cosecant of 90 degrees minus A. And we flip over tangent, we get cotangent. And flip over cotangent, we get tangent. These are not often used. Why? We hates them. These are our precious. We hates the other three. We hates them. Those dirty little hobbits. Little Lord of the Rings for you. All right, so let's do an example using these. Pause this if you need to. It's kind of fun. Sine goes with cosine, cosine goes with sine, and tangent goes with cotangent. So let's play find the cofunction identity, or cofunction. Find the cofunction. So examples. A, we'll do sine of 63 degrees. B, we'll do cosecant of 78 degrees. And C, we'll do cotangent of 39 degrees. Okay, so to find the cofunction angles, I'll do the first one, then I want you to pause it and do the others. The way to go about this is say this is cosine of 90 minus A, where this is A. So I've got cosine of 90 degrees minus 63 degrees. Cosine of 27 degrees is the cofunction. Notice I didn't put parentheses here. It's hit or miss whether people do. I'm going to do it now. Why don't you pause the video and try to figure out the other two? I will assume you did. Cosecant goes with secant of 90 minus A. So we have 90 degrees minus 78 degrees, which is secant of 12 degrees. And finally, cotangent goes with tangent. 90 degrees minus 39 degrees. 90 minus 39 is 51 degrees. That's how the cofunctions work. They can be handy. Note this whole sine, cosine, stuff like that. The way we're doing it, this is for right triangles. Because C has to equal 90 degrees for this to work. This approach, okay? This is only for right triangles. Okay. We can do some more fun stuff. Let's find theta. It's right there. Yeah, I know you've all seen the whole stupid find x and someone points at x on the triangle. That was me being ridiculous. So what we're going to do, our first example, we're going to do sine of 2 theta plus 3 degrees equals cosine of 4 theta plus 9 degrees. Okay, so if we say this is sine of A equals cosine of B, we're going to assume right triangle. Assume a right triangle. Then B equals 4 theta plus 9 degrees. It also equals 90 minus A. But A is there. So we have 4 theta plus 9 degrees equals 90 degrees minus 2 theta plus 3 degrees. You following me? All right. We should distribute that. We got 4 theta plus 9 degrees equals 9 degrees minus 2 theta minus 3 degrees. So what do we have here? I'm gonna add 2 theta to both sides. Get all my thetas on the left. I'll subtract 9 degrees over here to get it on the right. And we'll combine the 90, negative 9, and negative 3. I've got 6 theta equals 90 minus 9 is 81, minus 3 is 78. Divide by 6. Our algebra does not go away. 78 divided by 6 is 13. Theta equals 13 degrees. Not bad, not too hard. Algebra. It's all algebra. Recognizing what you need to do, though, it can be tricky. Can be tricky. You may ask, a lot of people ask, why trigonometry? Why do we need it? And I'm going to be honest with you. It's the heart and soul of most of the things you know. You're not even aware of it, though. When we get into graphing sine and cosine, they make waves. Just like ocean waves. But it's also like sound waves and light waves. And you'll find, if you go far enough down the rabbit hole, that any polynomial function you've done in algebra, like x squared plus 2x plus 1, can be written as a sum of sine and cosine angles with different thetas inside them. And since light and sound make up a lot, those are 2 of our 5 senses, sight and hearing. There are some really important things in what we study. Okay? So, trigonometry is important, so we got to learn it. Let me give you guys an example. I want you to pause the video when you're done or when I'm done writing it, and work it out, and then restart it, and we'll do it together. We have secant of 7 theta plus 12 degrees equals cosecant of 3 theta plus 8 degrees. Okay. Pause, work it out. Okay. I'm going to call this my A and this is my B. So 3 theta plus 8, which is B, equals 90 minus A, which is 90 degrees minus 7 theta plus 12 degrees. I'll distribute. It really just moves the negative into both of them. I'll add 7 theta to both sides. I'll subtract 8 degrees from both sides. Bring my equal sign down. 3 theta plus 7 theta is 10 theta. And negative 12 and negative 8 is negative 20. 90 degrees minus 20 degrees is 70 degrees. We divide by 10. We find theta equals 7 degrees. Some other fun stuff that you'll notice. Let's look at, I'm going to draw a portion of the unit circle. So fun facts about sine and cosine. For a fixed radius r, I'm going to use, let's use r equals 1 because it's the easiest one to see. When r equals 1, sine theta equals y, cosine theta equals x. And theta is going that way. Okay, this is a radius of 1. What happens as theta increases? Well, as theta increases, it starts here, y equals 0 right here, and it just keeps going up, 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 and up to 1. As theta increases, for 0 less than or equal to theta, less than or equal to 90 degrees, as sine theta, or as theta goes up, sine theta goes up. What's happening with cosine? Cosine is x. It starts as 1. And as we go up, the x value is going left, 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 left until it gets to 0 when it's 90 degrees. Cosine theta goes down. Okay, so sine theta is increasing from 0 to 90, and cosine theta is decreasing. Ready for some more? Actually, I'm going to write that for you in terms of r for any r. So for looking at 0 is less than or equal to sine theta is less than or equal to 1. We have 0 is less than or equal to y over r, which is less than or equal to 1. And we multiply by r on all sides. We have 0 is less than or equal to y, less than or equal to r. In that range, sine theta. For y between 0 and r, sine theta is increasing. As theta increases. And likewise, you can write out cosine the same ways. Let's take a look at our next section. Pause it for a second if you need to finish writing that. Our next section is on special triangles. So we're going to dump the right triangles. So our first special triangle we're going to look at is the equilateral triangle. In an equilateral triangle, all sides are of equal length. This forces all angles must be equal, must therefore be equal. And that means A plus B plus C equals 180 really turns into A plus A plus A equals 180. And you'll find out that A, B, and C are all 60 degrees. An equilateral triangle (60 degrees, 60 degrees, 60 degrees). Guess what? We can make a bigger triangle that has the exact same thing. Also 60, 60, 60. So here, the angle doesn't tell us anything about the sides. All equilateral triangles are similar. Fun. That's fun. I'll pause it, let you write it down. This leads to another fun triangle, though. Okay, I'll assume you paused it and wrote it. Let's say we've got that 60, 60, 60 triangle. And we bisect it or cut it in half. So that was 60 degrees. This is 60 degrees. This is 60 degrees. Cutting it in half makes this two right angles, which means we're cutting this in half. This makes this a 30-degree angle. This a 30-degree angle. If I just draw one of them, we have a 30, 60, 90 triangle. That's what it's called, a 30, 60, 90. The fun thing about 30, 60, 90 triangles is, if we call the side opposite 30 x, the hypotenuse is equal to 2x, and the adjacent side is x root 3. Okay? True for every 30, 60, 90 triangle. They're all similar, it just changes what x is. For x equals 1, like on a unit circle, we have 2x equals 2, and x root 3 equals root 3. Our triangle we have 1, root 3, and 2. Does that work? 1 squared plus root 3 squared equals 2 squared. Yep. 1 plus 3 equals 4. It does work. So what does that tell us about sine of 30? Sine of 30 degrees is opposite over hypotenuse. Sine of 60 degrees is root 3 over 2. If we look at cosine of 30 degrees, it's adjacent over hypotenuse. And we look at sine of 60, oops, I said, yeah, cosine of 30 degrees. Sine of cosine of 60 degrees, that's what I'm missing here. Cosine 30, cosine 60 is adjacent over hypotenuse is 1/2. Now this makes sense. Remember our cofunction angles? It matches up. We also pull from this triangle tangent of 30 is sine over cosine. And if you work that out, it's 1 over root 3, which is root 3 over 3. If we look at tangent of 60, we have root 3 over 2 divided by 1/2 is just root 3. Okay, we're going to use these on making a table in a little bit. These are all important. So 30 degrees are our most important angles, most important degrees, or angle measures. These come up commonly. 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees. We already know 0 and 90 from quadrantal angles. We just looked at and found sine, cosine, and tangent of 30 degrees and 60 degrees. Let's look at the 45. I'll give you a second to pause this, write this stuff down. We'll make a table in a second, compile it all together. Okay. So we need 45 degrees. If we're working with a right triangle, that's 45 degrees. This is 90 degrees. To get 180, this one also has to equal 45. So if this one's x, then this one has to be x. And we can figure out what that side is. Let's say it's r. We have x squared plus x squared equals r squared. We add them together, we get 2x squared. And if we take the square root of both sides, we get r equals square root of 2 times x, which we tend to write as x root 2. It's positive because it's a distance. x root 2. So again, we're going to let, for a unit circle, again, x will equal 1. So we have 1 square root of 2. This is 45. This is 45. You will see that by looking at this, the sine of 45 degrees is actually identical to the cosine of 45 degrees, and it's 1 over root 2, which is root 2 over 2. Tangent of 45, I'm not going to do sine over cosine. It's y over x. 1 over 1 is 1. Okay? So we can make a table. We'll put theta here, sine theta, cosine theta, tangent theta. I've got 0, 30, 45, 60, 90. Sine of theta starts at 0, ends up at 1. We know 45 is square root of 2 over 2. I'm going to write these other ones. I'm going to rewrite 0 as the square root of 0 over 2. And this is the square root of 4 over 2. And you're like, why the hell is he doing that? Right? Why would I say 1 equals the square root of 4 over 2? Because oddly enough, we were just looking at sine of 30. Sine of 30 was 1/2. Well, that's the square root of 1 over 2. And sine of 60 was root 3 over 2. So notice the denominator is 2 going on all of them, and the number inside the radical just goes up by 1. Cosine goes the other way. It starts off large, and it ticks downwards. Neat, right? And tangent of theta, I can write this as a pattern. It's not all that helpful. 0 equals 0. And this one's always undefined because it's sine over cosine and cosine 0. I can really write this as root 3 over 3 to the first power. And this is dumb. I wouldn't do this. But I'm pointing out, if you like patterns and this is for you, then this is exactly what you want. Oops, it's just the numerator is cubed. Let's try that again. Root 3 to the first power over 3, root 3 to the second power over 3, root 3 to the third power over 3. This is root 3 over 3. This is root 3 squared is 3. 3 over 3 is 1. And this is 3 root 3 over 3, which is just root 3. So I'm going to rewrite that. I don't like that messy table on the right. Let's take a look at it. This is easier to remember. Easier to do sine over cosine. Okay? It's just a little bit of fraction division. So I'm going to rewrite that table. And I think having the roots on these ones over here is good. So root 0 over 2, root 1 over 2, root 2 over 2, root 3 over 2, root 4 over 2. Here, it goes the opposite way. It ends up low. And you can go backwards like I'm doing here. Or if you start at 0, start at 4 and count downward. Zero, 1/2. This one stays a radical. This one stays a radical. That one equals 1. This one is just the exact same thing as sine theta in the reverse order. And here we've got 0, root 3 over 3, 1, root 3, and undefined. That's your cleaner table. Now, this is for angles. These are the cool kids angles, cool kids club angles. For theta when it's between 0 and 90 degrees. These are acute angles. Remember that from lesson 1? What about non-acute? Okay, I'm going to leave it up here for a second, pause it so you can write it down. We're going to look at this pictorially. Okay. So we have our first one. This was our acute one. And theta equals theta. When we're in quadrant 2, let's say we're going there. That's theta. I'm going to call this angle right here, I'm going to call it theta hat. So books, you'll see theta hat, you'll see theta tilde. You might even see theta prime with like an asterisk or a apostrophe on it. Okay, so that's theta hat. Here, theta hat, these two have to add up to 180. So theta hat is 180 degrees minus theta. Okay. Oops, black line. Let's look at each of the other two quadrants, quadrant 3 and quadrant 4. So here is theta, and here is theta. We want these angles right here, this theta hat, or whichever one they use, theta tilde, theta prime. This is called the reference angle. The reference angle in quadrant 3, you go back to the x-axis. This is theta hat, that angle right there. or really right there. It's from the x-axis. And same with here. From the x-axis, theta hat. So in this quadrant, the full thing is 270 degrees, I'm going all the way around, right? Or I could say theta hat equals, well, this whole thing, let's go with theta. Theta equals 180 degrees plus theta hat, right? Theta is this 180 plus theta hat. So theta hat equals 180 degrees, or theta minus 180. And here, if we go all the way to all the way around, it's 360, but then we got to subtract theta. So theta hat is 360 minus theta. Okay. It's important to note all reference angles are from the x-axis. Do not go off the y-axis. It's always off of this x-axis. Okay. So I'm going to draw a big picture for you for just, I'm going to compare it in quadrant 2 to illustrate what's going on. Let's see, can I get the same angle? Nope, a little bit further. There we go. That's theta hat. This is theta. This is x. This is y. You'll notice this has the same y value. So this is y. And to keep the triangles the same, this has got to be negative x. How does that work? Over here, let's look at sine theta, cosine theta, and tangent on both of them. Cosine theta hat, tangent theta hat. In both cases, it's the same radius. If I just kept rotating the line around. Over here, we have y over r, x over r, and y over x. Over here, we have y over r, negative x over r, and y over negative x, which is negative y over x. For all the reference angles, you'll notice something. I illustrated it with the one in quadrant 2. For all the reference angles, sine theta hat equals sine of theta. Cosine theta hat equals cosine theta. And tangent theta hat equals tangent theta, other than maybe a sign change. Possible sign change. So here, sine didn't actually change signs at all. cosine theta, it changed signs. It was positive x over r. Now it's negative x over r. Here, went from positive y over x to negative y over x. And if we really wanted to reference theta in terms of a reference angle in the first quadrant, theta hat actually equals just theta. It's the same angle. They're identical. So for all those angles, let me write down the list again. Quadrant 1, theta hat equals theta. Quadrant 2, theta hat is 180 degrees minus theta. Quadrant 3, theta hat is 180 degrees. Or, I'm sorry, theta minus 180 degrees. They just switch. Quadrant 4, theta hat is 360 minus theta. Okay. Minus theta. Let's use this to find reference angles. So, some problems. Find theta hat. We're going to do 162 degrees. We'll do it together, and I'll have you do these other ones on your own. Well, this one is in 162 degrees, is between 90 and 180. So we're in quadrant 2. So this is the 162 degrees. That's theta hat. Theta hat is 180 minus theta. Theta hat equals 18 degrees. Go ahead and try to work out B. And C is your challenge problem. I'll assume you paused it. And we'll go on. 250 is between 180 and 270. So it's quadrant 3. Down there, we have theta hat equals theta minus 180 degrees. Theta hat equals 250 minus 180 degrees. So theta hat equals 70 degrees. Clearly my picture should be a little bit wider because 70 degrees is a big sweep. What about C? Oh, this was a tricky one. First, you want to get it to the least positive angle. So let's just keep subtracting 360. That's 765, or minus 300 would be 765, minus 60 is 705. Subtract another 360. And what is that, 335? 345. 345. There we go. That puts it in quadrant 4, which makes theta hat right there. Theta hat in quadrant 4 is 360 minus theta, minus 345. So theta hat is 15 degrees. Why do we care about doing any of that? I'll show you. It makes it really easy to find all of our sine, cosines, and tangents. So this is going to pull things that we did earlier, several things we've done in this hour. Find the exact value, which means I don't want decimals, no calculator, or anything like that, of the 6 trig functions for theta is 240 degrees. Okay, so pause it if you can. Try to figure this out. If you're not sure what to do, just keep playing and we'll do it together. If you can try to figure it out, compare yourself with what I'm going to do, that's great. 240 degrees is between 180 and 270, which means it's in quadrant 3. Theta hat. What is theta hat in quadrant 3? It's theta minus 180. Theta is 240. So 240 minus 180. Theta hat equals 60 degrees. We are in quadrant 3. What are the signs of sine theta hat, cosine theta hat, and tangent theta hat? Well, no, just sine of theta, cosine theta, tangent theta. We're in quadrant 3. Sine theta is less than 0. Cosine theta is less than 0. Tangent was the only one that's positive. All strippers take cash, remember? So when we're going through these, the sine of 240 degrees is the same thing as the sine of its reference angle, 60 degrees, but it's got to be negative. And that's by quadrant. And what's sine of 60 degrees? Well, this was one of our special angles, 0, 30, 45, 60, 90. Sine of 60 degrees was root 3 over 2, which makes sine of 240 negative root 3 over 2. If we look at cosine, this is the same thing as the cosine of its reference angle, other than a potential change in sign. Quadrant 3 does make it change sign. It becomes negative. Cosine of 60 degrees was 1/2, and the negative makes it negative 1/2. And finally, tangent is the same thing as tangent of 60 degrees. Tangent of 240 is positive, so was tangent of 60. What was tangent of 60? It's sine over cosine. It's equal to root 3. Now we just flip these for our reciprocal angles. Cosecant of 240 degrees is negative 2 over root 3. And to write it correctly, we'll write negative 2 root 3 over 3. Secant of 240 flips over cosine. Flip over cosine, negative 2 over 1. It's just negative 2. And tangent of cotangent of 240 degrees is equal to the cotangent of 60 degrees. It's the same sign. We flip over tangent. It's 1 over root 3. We rationalize it, we get root 3 over 3. That's all 60, or all 6 trig function values. What did we do here? Determine the value. And then determine sine based on quadrant. Okay. So we can write out a list of general steps. I don't know if you like this. Some people like a recipe. An algorithm is what they call it in math and programming. So general steps for any old theta. Step 1. If theta is not the least positive angle, find the coterminal angle that is. By adding or subtracting multiples of 360. Step 2. Find the reference angle. I don't care if you call it theta hat, theta tilde, theta with a dash. Some people even do theta bar. All of these are good runners up, good choices. We're going to use this one. Every once in a while, I slip and use that one. So those are the two I use. Step 3, find the trig values for theta hat. This one sucks. This one looks like minutes. Like the degrees, minutes, seconds. But when we get to radians, we don't have minutes, and it's confusing. So don't use that theta apostrophe. That one sucks. So we find the trig values for theta. And finally, step 4, determine the sine. Based on the quadrant of theta hat. Where is it at? Or I'm not sorry, not theta hat, the coterminal angle, the one we got in step 1. Okay. Pause it for a second. That's what we're going to do. We'll run through some examples. I got 2 examples, and I want to talk to you about using your calculator. Okay. I'll assume you paused it and are ready. We're not going to find all 6 values. We're just going to find the sine of negative 210 degrees. So theta equals negative 210. We don't like that one. It's not the least positive one. Add 360 to it. And we get the coterminal angle is 150 degrees, which puts it in quadrant 2. Actually, it goes all the way around. But, oh, it goes the other way, really. What am I doing here? It's really going that way. That's the negative 210. This is 150 degrees. What is this angle right here? That's our theta hat. It's 180 minus the 150. Or another way of thinking about it is they have to add up to 180. What do you add to 150 to get 180? Theta hat is 30 degrees. Or it's 180 minus the 150. So that was step 2. Let's find the reference angle. Step 3. So this was step 1. This was step 2. Step 3, find the trig value for sine theta hat. Sine of theta hat is sine of 30 degrees. And if we memorized our table, we don't need to look at it. But if you haven't memorized it yet, look at the table, it's 1/2. Step 4, we go back to our original angle. Sine of negative 210 has to equal the same value. Now just check for quadrant. Quadrant 2, sine theta is greater than 0. So it's positive. That's our answer. Okay. Why don't you guys try the next one? Hit pause and we'll go through it together. Find cotangent of 480 degrees. I'll assume you hit pause and we'll go with it. Step 1. We don't like 480, it's too high. 480 minus 360 is 120. This is our coterminal angle. Step 2. What's theta hat? Let's draw a picture. 120 degrees is a little past 90. Which makes theta hat the rest of the way to 180. Theta hat has to equal 60 degrees, or 180 minus the 120. So theta hat equals 60 degrees. Step 3. We want cotangent of 60 degrees. I don't have this table memorized, but I do have the cosine and sine memorized. Cotangent is cosine over sine. Cosine of 60 degrees is 1/2. Sine of 60 degrees is √3/2. This ends up being 1/√3 or √3/3. Finally, I check quadrant. In quadrant 2, sine theta is greater than 0. Cosine theta is less than 0. which means cotangent theta, which is cosine over sine, is less than 0. And so cotangent of 480 degrees, our initial angle, has to equal the negative version of that, negative root 3 over 3. Okay. Now, it's really important that you have these memorized because, let's be honest, you only have a certain, even if we just look at this right now as being a student in mathematics, you only have, when you get to, right now, you're going to have a lot of time. I'm going to give you a lot of time on the test because we're going to be online. You need more than the time I want to give you. But in a regular class, like when you get to calculus, you're going to have a limited amount of time. And you do not want to have to pull out your calculator to find out every stupid basic angle when all the basic angles are easy to memorize. It's a simple pattern. Make flashcards. Do I have my stack of flashcards in here? I don't think I do. I'm going to have to bring them in here and show you my stack of flashcards that I built as a student at COS. I was a student here at COS. I'm sure I said that during orientation, but I have a stack of flashcards that's like that big. I was cheap. I was budgeting. I'd take a 3x5 card and I would cut it up, make it like a cross out of it, cut it into like 4 pieces, make 4 small ones, and that way I'd get 4 flashcards out of one 3x5 card. It works. So something I want to tell you, talking about using calculators, let's take a look at what calculators have. This is my calculator. I don't know that you can see it, but right now up here, it says in a very small letter, D. So using calculators. It's important to know most calculators come with a DRG option. D is for degrees, which is this chapter. R is for radians, which is next chapter. And we use these a lot. These are the 2 we use. I suspect Europeans use G. G is for gradients. You'll never use this one. You'll likely never use this one. I never have, and I've done a lot of mathematics. The idea of it is, just so you know, one grad is 9/10 of a degree. What this does is it divides a circle into 400 parts. So each quadrant is 100. And the metric system likes using multiples of 10. I'm sure that's where they do it. And you use it is in European countries or places with metric system. My calculator, I have to hit mode, and then I got to hit mode again. Degrees, radians, and gradients. Okay, so it's important to identify which mode your calculator is in. Sine of 30 in degrees is 1/2. Sine of 30 in radians is not 1/2. So it's important that you have the right method in there. Okay? When you're using a calculator, pause it if you need to write this down. I don't even know if that's the right spelling of gradients, to be honest. I've never used it. So when using this, when using a calculator, convert minutes and seconds to decimal. To decimal degrees. For example, cosine of 22 degrees, 36, I put a comma in, you don't have a comma in there, 36 minutes, 50 seconds. We convert to decimal first. This is 22 degrees plus 36 minutes. And we multiply by 1 degree is 60 minutes. And then we have 50 seconds. And we have 1 degree is 3,600 seconds. And when I do this, this is 22.6138 bar. I'm literally going to put that entire sequence in. This line right here. 22 plus 36 divided by 60 plus 50 divided by 3,600. 22.6138888889. At this point, if I do this operation, my calculator stores it as the answer. Likely your calculator has something similar. I have a key on here that says answer. Sine, cosine, and tangent are on there. If you want to use cosecant, secant, or tangent, you have to use reciprocals, and I'll show that in a second. I'm going to do cosine of my answer though. Cosine, rather than typing that in, it's already stored. Cosine of answer, 0.923 117034. Okay. Speaking of the weird ones, the ones we don't like. Cosecant of 142 degrees. You have to recognize this is 1 over sine of 142 degrees. All clear. 1 divided by sine of 142 is 1.624269245. And then if you're asked for a certain number of rounding places, obviously do that. We got some more calculator options we're going to go through. This is when we're working with the inverses. So it's important to note when we say if sine of theta equals some value A is a number. And we can write theta equals sine inverse of A. I don't know if your calculator has it. I don't know if I can get this close enough to show it. Above sine, my sine key, I've got sine -1. That's an inverse option. It's in yellow. I have to hit the shift key to access it. Okay. For now, we will treat theta for this section in your homework. Theta is in quadrant 1. Okay, so our example, if we say cosine theta equals 0.923, rewriting it like we do up here, theta equals cosine inverse of 0.923. On my calculator, I hit shift and then cosine. And then I type in 0.923. Okay. Shift cosine. Notice it pops up the cosine -1, cosine inverse. Theta equals 22.63132136. And obviously we would round it wherever we want to round it to. The inverse ones are the pain in the ass for especially cosecant, secant, and cotangent. So let's look at one of those. Cosecant of theta equals 1.63773808. This means sine of theta equals 1 over that. And this means theta equals sine inverse of that. You either want to do this operation first and then do sine inverse the answer, or you got to use the parentheses key. I'll use the parentheses key. So I want shift sine, and then I'm going to say parentheses 1 divided by 1.637733808 end parentheses. And what do we get? 37.6. Okay. And that kind of wraps up 5.3. Any questions? If you've got questions, come to office hours or email me. We will, for the summer session, we'll be doing it during our normal class hours, and you can watch these videos at your leisure. But as for now, peace.